This is another video dedicated to the environmental behavior of persistent organic pollutants. In this video, I will be discussing what partition coefficients are, and I will be discussing their uses to predict behavior of pollutants and their strengths and limitations. We need to track when a persistent organic pollutant moves throughout the environment. We need to be able to predict where will it move. If you think of, for example, a pesticide, a chemical that you could potentially use as a pesticide or a herbicide, it is important to monitor where that chemical will go. Will it stay in the soil? Will it be absorbed? We will move to the water and potentially enter aquatic species. Will it be absorbed by the plants? Will it volatilize and become a gas and then move away by the presence of winds and appear somewhere else? And we do that, or a way to do that, is using something called partition coefficients. Partition coefficients are equilibrium distributions. It monitors how a single substance, the chemical you're interested on, partitions between two solvents. And the solvents can be liquids or gases, and we call them solvent phases. And they can be a pure substance, or it can be a mixture. So for example, air would be a mixture of gases, or they can be pure substances. And the idea is that those two phases are non-miscible, that there is a boundary between them. Think of oil and water, for example. There is a physical separation between the two phases, and the partition coefficient measures how easy it is for that pollutant to go to one or the other other phase. They're also called distribution coefficients because they literally follow how a chemical distributes between two phases. The most famous one, or the first one used, is the gas-liquid one. And it is the only one that has a proper name. It's called Henry's constant. It's also known as a simple solubility of gases. And it's the one that studies how easy it is for gases to dissolve in water. And the most common one, or the most useful one, the one that is used in the environmental arena more often, is the liquid one, and it's called the partition coefficient octanol water. So starting historically from the first one, the gas liquid, Henry's law. If you imagine a system in which you have two phases, and your two phases for this partition coefficient are going to be air and water. And you imagine your chemical, and you're going to have a chemical X. So if you have your chemical X imagine a closed vessel, the chemical cannot go anywhere, it stays there, trapped. There will be a certain amount of your chemical in the water, and there will be a certain amount of chemical in the air. And because the chemical in general cannot go anywhere, it's trapped in that imaginary vessel. The particles of X in the air and the particles of X in the water will change depending on whether X is more soluble in air or more soluble in water, but there will be a moment in which you will reach an equilibrium. As much as X will be in the air as it can possibly be, as much as X will be in the water as it can possibly be, depending on the chemical nature, depending on the compound X itself. So we defined, or Henry's law, partition coefficient gas liquid is refined, KH, as the concentration of the chemical in water divided by the concentration of the chemical in air. And we give this concentration not as a units of concentration like moles per liter or grams per liter or something like that, but as a units of pressure, the partial pressure of that chemical in air. So that is Henry's law. And it's called also simple solubility, or solubility of gases. And this is just a table of the partial pressure of some known gases and Henry's constant for those gases. And if you see, it has units. two things. First of all, Henry's constant has units because it's a mixture of units of concentration divided by units of pressure. And second, look that I've mentioned the temperature. And that is because the solubility of your chemical will change with temperature. Sometimes gases will be more soluble with increasing higher temperature and less soluble at lower temperatures, and sometimes will be the opposite. In general, it is the opposite. The warmer the water, the less soluble the gas is. And you might think of, for example, when you're boiling water to make pasta, if you watch water being boiled, you will see that there is some moment where you start seeing some bubbles leaving the water. What you are seeing is the oxygen leaving your water, and that happens at around 80 degrees. So when you increase the temperature, the oxygen is less soluble in the water, and what you are seeing is not the water boiling, but your oxygen molecules leaving the water. The octanol water partition coefficient is by far the most common one and the most useful one, and the one that is used for almost everything. It's the liquid-liquid partition coefficient. It measures how easy your chemical of interest, X, partitions between two liquids. And the two liquids that is defined of are octanol and water. An octanol, it's a proxy for fatty tissues. So an octanol water partition coefficient tells you how easy or difficult is for your chemical, or for the chemical you're looking at, to dissolve in the fatty tissues of, let's say, an aquatic animal. If you have that chemical in water, how easy will it be for that chemical to leave the water and enter your fish, your aquatic species, into the fatty tissues? And is defined as the concentration of the chemical in octanol divided by the concentration of the chemical in water. It has no units, it's dimensionless, because you are dividing two concentrations. So the final constant, the final partition coefficient does not have units. And you can use any units of concentration you want, moles per liter or ppms or grams per liter. The final number, as long as the two concentrations you are using are in the same units, will be dimensionless. And it is by far the most common one. Originally, it was used in the pharmaceutical industry, and it's one of the things that you give of your about your chemical if you are describing it, your pharmaceutical compound. Another one that can be quite useful is the organic carbon water partition coefficient, and it tells you how easy it is for your chemical, how easy it is for the chemical you're interested on to be retained in the soil, in the organic matter of the soil. And it gives you an indication of the ability of the chemical to leach through the soil and to get into the water. And then once it gets into the water, to be uptaken, A, to move out of the soil and into a water body, and B, to be uptaken by plants and animals from the soil and sediments. The tendency of leaving the soil. The partition coefficient organic carbon water increases with molecular weight. And as with all the other examples I've given as all partition coefficients, it is what we call a thermodynamic constant, and that means it depends on the chemical you are studying, the structure, the chemical structure of that particular compound, but it also only depends on the temperature. So yes, at different temperatures, you will have different organic carbon water partition coefficients. The next one, reasonably common, is the octanol air partition coefficient. And this can be useful to describe how a chemical, let's say, for example, in this case, a pesticide, will move from the plant lipids to the air surrounding them, and therefore fly away, move away, volatilize. And it can be, you can play with these partition coefficients by combining them. For example, the partition coefficient between octanol and air can be defined as the partition coefficient between octanol and water and the partition coefficient between air and water. And the partition coefficient between air and water is Henry's constant. And they are, well, they've been well tabulated. They are in Henry's constant came for the first time in the 19th century. So another nice thing you can do with partition coefficients is that you don't have to measure them all. You can have some of them and then combine them to produce new partition coefficients for other things you are interested. So when you're looking at a chemical, by knowing, for example, Henry's constant and its octanol water partition coefficient, you can then combine them to produce other partition coefficients that again will explain you. When your chemical is in the environment, will it be will it move preferably to the water? Will it stay in the soil? Will it volatilize and move to the air? Will it enter the food chain? Will it enter the fatty tissues or of animals, or the lipids or in plants? So that's sort of that's the role of partition coefficients. Keeping track when you are interested in a chemical. Where are you more likely to find that chemical? If you have to take certain decisions about taking samples in the environment, let's say there is a chemical spill of a chemical of concern, of a pesticide or a potentially toxic chemical. Once it's out in the environment, where will it go? Will it go straight to the air? Will it stay on the soil? Will it move to the water? Will it potentially enter the food chain? And the nice thing of partition coefficients is that they are thermodynamic constant and you can all use them. They are well tabulated and they will you can take certain decisions about the movement of pollutants throughout the environment without having to necessarily take many samples. You can be more informed when you take your samples because you will know that your chemical will be most likely in one or other parts of the environment, the soil, the water, the plants, the animals. You can use persistent organic pollutants by to do some simple modeling you can use partition coefficients to do some simple modeling of the behavior of a persistent organic pollutant. They are just that, a model. It assumes some very, very simple, it's kind of a simple model. For example, I've got here an example of what would happen to a chemical between water and a fish. You imagine that your two phases have one defined boundary, that there's no mix between both, that there's only one way to access that body. For example, you imagine that your fish is intaking that chemical through the water, through the body, through the skin. You don't take into account that it's being swallowed, that it gets into that it's being eaten through its diet. So again, it's a simple model, but it can help you predict very easily and roughly where will that chemical go, roughly where it is more likely that chemical will be found. And again, it does depend on temperature, but that's kind of the key point. Other than that, you can do some modeling, but some simple modeling without having, again, to go to the environment and take samples and analyze the samples. So it's kind of a quick and dirty way of predicting the behavior of your chemical in the environment. Some definitions: bioaccumulation, biomagnification, bioconcentration, and bioconcentration factor. They all sound slightly similar. They sound very similar, but they look at slightly different things. Bioaccumulation looks at how an organism will take up and retain a particular chemical, a pollutant. And it depends on the rate of intake, how easy it is for the organism to take up the chemical, how fast it happens, versus the rate of elimination, let's say through urine or feces, and also the rate of elimination through breaking down by metabolic pathways. Biomagnification is when a chemical has entered the food chain and it becomes concentrated as you go up the trophic levels of the food chain, which eventually finishes with us humans. Bioconcentration is looks at the concentration of a chemical in a particular organism compared to where that organism lives. So, for example, how a chemical will enter a fish. A chemical dissolved in the water will enter an aquatic species that is living in that water. And you define bioconcentration factor as the measure to quantify how a chemical will accumulate in a particular organism. Bioconcentration factor and bioaccumulation factor are slightly different. So bioconcentration factors refers to the levels of the chemical in an organism, and only due to uptake from the surrounding water. While bioaccumulation factor also looks at how much of the chemical enters the organism, including uptake from food. So bioconcentration factors can only be measured in laboratory studies because it's where you can control the amount of food and the food that organism is eating. And typically when you measure ratios in the field, when you, let's say, take fish samples and measure the concentration of a particular chemical, and you have got that fish from the field, what you are measuring is bioaccumulation factor, because you do not know how much has entered just through contact of the fish with the surrounding water, and how much has been uptaken by food. So this is all for this video, and I hope it was useful. If you have any questions, again, please email me or post in the chat. And thank you very much for watching.